The growing amount of space debris is an increasing concern due to the risk of collision. Hypervelocity impact testing facilities are crucial for research and design of shielding to protect spacecraft and humans in orbit. Therefore, we have designed a light gas gun facility capable of accelerating a 1 gram aluminium projectile to velocities above 7.5 kilometers a second, a speed equivalent to travelling from Southampton to London in less than 15 seconds, and firing the projectile into targets up to 65 centimeters in diameter. Controlled remotely to ensure safe operation of the facility, the pendulum ignites the charge in the combustion chamber. The resulting explosion increases the pressure in the combustion chamber and pushes the piston along the pump tube. The piston then compresses the light gas in front of it until the gas reaches a pressure of 100 megapascals, which is equivalent to the pressure of a small car balanced on the area of a pound coin. When the rupture disc breaks, the resulting pressure on the projectile propels it down the barrel, where it accelerates to hypervelocity speeds. The interior of the barrel in front of the projectile is under a vacuum to more closely mimic orbital conditions and increase the speed achieved by the facility. The barrel is also segmented to overcome manufacturing constraints, and this modular design increases the maximum length and thus velocity range achievable. The projectile exits the barrel after 2 milliseconds and travels freely in the flight tank, where the servo separates due to the spin induced on the servo within the rifle barrel and is caught on the stopper plate. The projectile passes through a set of light gates which measure velocity before entering the impact chamber where the target is housed. All of this is done in under 2.4 milliseconds, more than 4,000 times faster than Usain Bolt can run 100 meters. After the flight tank, the projectile breaks both of the laser beams, which is picked up by sensors, and from this the velocity of the projectile is calculated. After the first beam is broken, a signal is relayed to the high-speed camera to start recording. The debris from the impact is illuminated by a laser sheet and imaged at up to 1 million frames per second by the high-speed camera. Finite element analysis was used alongside analytical calculations and modelling to ensure all projectiles and fragments involved are safely contained. We have developed comprehensive models to predict the temperatures and pressures within the gun, and therefore the piston and projectile speeds. We optimised the gun parameters to maximise projectile velocity and reliability. And while the model started with basic assumptions, we introduced additional complexity and steps, to the point where the model predicts performance to a degree of accuracy greater than some published models. This project met the design aims of projectile mass and velocity and target type, and we truly believe that this facility will add valuable research capabilities within the university and to the UK space industry as a whole.